Now that we've had a look at conditional statements in our introduction to proofs and reasoning, we're going to take a look at what are called biconditional statements and definitions. A biconditional statement is a statement that combines a true conditional and its converse into a single statement or a single item. Now, when we do this, in notation, we will have a double arrow. So P, Q. This will read P if and only if Q. Another way of doing the, instead of writing out if and only if, is to simply say if spelt with two F's. So if I see P if with the double F Q, it says P if and only if Q. And we can take definitions, or we can take conditional statements that have true converses and write them as biconditionals. So example, if two angles have equal measurements, then the angles are congruent. So our P statement, our hypothesis, is two angles have equal measurements. And from that, our conclusion is the two angles are congruent. Now, it is the case that if two angles have equal measurement, then the two angles are congruent. But also, if two angles are congruent, then the two angles have equal measurement. So both the statement and its converse are true. This means we could say two angles have equal measurement if and only if the angles are congruent. Now, the single cell comic here, honk if you love formal logic. So our conditional here, or our hypothesis, is a person will honk their horn. The conclusion is that they love formal logic. And this is stating that if you honk your horn, then you love formal logic. It also states that if you love formal logic, then you will honk your horn, thereby implying that you will honk your horn if and only if you love formal logic, thereby implying that if the person is stopped at a red light and it turns green and they don't go right away, you don't start honking your horn just to get them to move. You only honk your horn if you love the formal logic. Now, this comic is from a website called XKCD and can be found online. So, citing my references for good measure. Now, when we have these biconditional statements, being able to deconstruct a statement into its pieces becomes very important. We got a little bit of a head start with this in our introduction to conditional statements, but let's take a look at it in this context now with biconditionals. So two numbers are reciprocals if their product is 1. So let's break this down into its pieces. So now the first part of the statement, our hypothesis, is two numbers are reciprocals. That's the first part of our biconditional. The conclusion is that the product of two numbers is 1. And it is the case that if two numbers are reciprocals, then their product is 1. And also it is true that if the product of two numbers is 1, then the numbers are reciprocals. So take it, break it down into its pieces, word it appropriately so it makes sense in English, and then give your statements. Next one, two angles are complementary if their sum is 90 degrees. Again, breaking this down, we take our first part of the statement, two angles are complementary, and we make that our P statement. Then we take the other part, their sum is 90 degrees, and word this a little bit with the sum of two angles is 90 degrees. So now, if two angles are complementary, then the sum of the angles is 90 degrees. And also, if the sum of two angles is 90 degrees, then the angles are complementary. It works both ways. And this is how definitions are developed. The requirements for good definitions are as follows. First, definitions use clearly understood terms. No ambiguity, no large vocabulary. They need to be very straight and to the point with words that everybody will understand. Second, the words of a definition are very precise. There's no kind of, maybe, bigger, because these words are subject to a person's opinion. Can't say short, because what's short to one person may not be short to another. So the words and terminology are very precise. Last, definitions have to be reversible. A definition is a biconditional statement. If it works from one direction, it has to work from the other. And we've run across theorems and postulates already that both the theorem and its converse are true. Those were actually biconditional statements. So let's take a look at a couple here and see how they are for definitions. A straight angle measures 80 degrees. First, we need to deconstruct this into its pieces. So, an angle is a straight angle becomes our hypothesis, and our conclusion, an angle measures 180 degrees. We examine, will this work? An angle is a straight angle. If an angle is a straight angle, then the angle measures 180 degrees. If an angle measures 180 degrees, then it is a straight angle. The reversible nature of this is true, so condition 3 is met. Precise, we have an exact amount of measurement, 180 degrees. And the terms, angle, straight angle, measurement, degrees, these are all items that are understood and accepted as basic vocabulary. So this does make a good definition. Let's take a look at number 2. A rhombus has exactly 4 congruent sides. So break this down into its pieces. We will arrive at a shape as a rhombus is our hypothesis, and our conclusion, a shape has exactly 4 congruent sides. So if a shape is a rhombus, then the shape has exactly 4 congruent sides. That is true. If a shape has exactly 4 congruent sides, then the shape is a rhombus. In the world of quadrilaterals, this is true. So as far as quadrilateral definitions is concerned, this would work. If we were to expand it out to other shapes, it would be possible for us to create a pentagon with 4 congruent sides, then 1 non-congruent. This is not a rhombus, but it meets the other criteria. So if we have a restriction added in, this would work. Otherwise, we would have to say no good. So let's take a look at a couple other definitions and see how they stand up to this criteria. So our first one, a fish is an animal that swims. Is this a good definition? Well, swimming, animal, fish are all good, clearly understood terms. It is precise. We don't have any general terminology here, but it is not reversible. I know how to swim, and I am not a fish. Therefore, this is not a good definition because it is not reversible. Rectangles have 4 corners. Well, that is true. Rectangles do have 4 corners, but corner is a little bit vague. Some people might say a corner is where 2 line segments meet. Others may imply that's 90 degrees. Because I can make a general parallelogram that has 4 corners, but it is not a rectangle. Some may say, well, it meant 90 degrees, but didn't state that, so this is not a good definition. Next, a penny is a coin worth 1 cent. Penny, coin, cent, all basic vocabulary. It is precise. We don't say it's a small amount of money, we say it's worth 1 cent, so we have an exact monetary value. And it is reversible. If I have a coin that's worth 1 cent, then it is a penny. If I have a penny, then there's a coin worth 1 cent. So this is a good definition. Last, giraffes are animals with very long necks. Giraffes, necks, animals, these are all good terms. Reversible, if an animal has a long neck, it's a giraffe. If it's a giraffe, then it's an animal that has a long neck. That comes into question because it's not very precise. What is meant by very long? As far as humans are concerned, very short-necked animals, a dog could have a long neck. And a dog is not a giraffe. Long neck or very long neck is a term that's up for discussion, so this would not be a good definition. Think of some of the definitions that you use in your everyday life. Do they meet these criteria? We're going to be looking at and examining definitions a lot throughout the course of geometry and into future mathematics courses. So make sure you have these ideas of biconditionals and definitions down pretty solid so we're ready to move forward and use them in our proofs and reasoning.